Hello and welcome to Lecture 8. Today we're going to be talking about this fancy concept called pointers, which is supposed to be one of the hardest things that you can learn when you're learning the C++ or the C language. So if you get anything out of today and anything at all makes sense, you should feel very good about yourself because this is a hard topic. Okay? So the first thing that I want to talk about is a while back there was a student who was a tutor, and he took some notes starting about halfway through one of these CS16 classes, and the topics are mostly the same. So if you want to click on any of these, they contain notes taken by somebody who's already taken this kind of class, and they might be helpful for you. So please take a look at those. Those are under the information section, and then notes from a previous class. Okay. So let me get out of that and let's go on into it. So why do you want to learn about pointers? Well, they're the lowest level. They're a way to talk about memory and access it and do very, very low level things. It's quite powerful, lots of indirection, but it's also a bit difficult. And if anything, besides learning about the underlying way that memory is arranged in your computer, you'll at least by the end of this lecture understand this, this old comic. So let's get on into it. Here's something that we have talked about a little bit before, but I want just to refresh your memory on it. So go ahead and pause this video and see if you can figure out what's going to be printed out by this code. And the idea is this function, we want it to swap x and y. So at the very end, we'd like it to print out, please. Initially, it'll print out 30, 40. And then at the very end, after we call the swap function, we'd really like it to print out 40, 30. That's what swapping would do. It swaps the values that are in those variables. Okay, so assuming you've thought about this, let's figure out why it is not what we expect. So let me go to code, or actually let's just draw this. Let's draw the stack diagram, because that's something we're going to learn to love if we haven't already. So here's our main function. And we make some local variables in our main function. We have a and b. So a holds 30, and b holds 40. And then from main, we're going to call this swap function, or swap values function. And we're going to pass along a and b into x and y. Now, the swap value function itself, I'll just call it swap, it has some local variables for itself. It has x and y, the parameters are also considered local variables in this case, and also it makes a variable called temp, tmp. So those are all memory that belongs to swap. Okay, so it has x, it has y, and it has tmp. So space gets made for that. All these three variables initially when you call the swap function. Okay, and so x is initially going to be set to whatever a was, and b is going to be set, y is going to be set to whatever b is. So we get 30 and 40 here. Okay, and then tmp will hold initially x. Okay, so then we have this kind of idea going on, and then we're going to set x to be y. So whatever, x becomes whatever y was, so now x becomes 40, and then y becomes whatever temp was, and so y becomes 30. And you can see now, once this function returns back to main, so this goes away, and we start printing out the values of a and b, well, they didn't get touched at all, and so we're going to just see the same values that we initially printed out, because this is all down in the main function where we're printing out these things. If we were to have printed out x and y while we were still in this function, in that case we would have seen different values, but we cared about a and b getting swapped, not x and y. Okay, so a is exactly what happened here, and that's not what we wanted, and pointers is actually one way to get around this. So a pointer is just a variable, it's another kind of variable, and it has a special kind of type. It has stars in the type. And a pointer is just a variable, and it contains the address of another variable. So the values that pointers hold, so the values that pointer variables hold are addresses of other things. So you have to be quite specific when you make a pointer. This is declaring a pointer. You say the type, then a star, then the name of the pointer. So I want P to be a pointer to an integer. It can only hold addresses of integer variables. And so you have to be very specific about the type of addresses you want to hold. Okay, so let's put this here. And this is the above is saying that, is declaring a pointer called P that holds the addresses of, it holds a single address at a time, so let's just say it holds an address that can hold an address of an integer variable. So if I had another int lying around, like if I said like int y or something, I could let P eventually hold the address of that variable y. That was an integer itself. And you kind of read this backwards. You say that P is a pointer. The star in the type you can read as is a pointer to. So P is a pointer to an integer. Okay? So that's just new syntax. And initially, if you just say it like this and you don't initialize it, of course it's going to be set to something that's completely random, just like any other variable. So P, if we declare it like this above, it's just going to hold a garbage value. And the values that pointers hold, remember, are addresses of other things. So this is just going to be in a like a garbage address. Okay, that's all that is. And so we should give it a value. There's a special kind of value that is initially a place that we don't have access to. So if you give P a value of 0, that's a special kind of address. So 0 or null with all capitals or null PTR in lowercase is called the null pointer. It's, let's make a new sentence here. It's an address that you don't have access to. So you can consider 0 to be the null address, the address of the null pointer, and 0 is a place in memory that you cannot access. It's always an error to access it. So null is a good initial value for a pointer that you don't know what to point to yet. You don't have a place to point to yet. Okay, so that's a proper initialization. You shouldn't try and use this pointer because, again, this memory address you don't have access to. And we'll talk about using pointers in just a few slides. So the word pointer should be a little indicative of what it does. We say it points to something. It points to the variable whose address it stores. Okay, so if I declare int star p and I have another integer, because p is a pointer to an integer, it is able to hold addresses of integer variables. Oh man, do I have an integer variable? I can eventually make p hold the address of this y here. Okay, and so if we want to make p hold the address of y, we'll use this address of operator ampersand. All right, so that's a lot of words. Now let's talk about how to do that in code. So if I say this, int star p, and if I say int y equals 3, well, these two lines, they make space in memory for us. One's for a pointer to an integer called p, and the other is just a normal integer called y. And it's important to think about these places as boxes in memory, and they each have their own address, right? Because with each value, there is a corresponding address of that value in memory. Okay, so let's say that p lives at address lives at address 100. That's the start of p. And then we can also say that y, let's pretend that it lives at memory address 112. This could be either hex or decimal, doesn't really matter for this purpose. But y is initially going to hold 3, and the idea is we want p to hold the address of y, which is not the value 3, but the address 112. So let's just say it's 112. We want to set this up, okay? Because right now, initially, p is undefined. we'll use the address of operator to do that. We'll say that P equals the address of ampersand Y. Okay, so let's talk about that. Ampersand, read that as address of, is the address of operator. Ampersand Y in this example is 112. Okay, so after I do this, P becomes set to, it holds the value, and P is a pointer to an integer, which means it holds the address of some other integer variable. Here's Y. I'm going to get its address and set P to be that thing. Okay, so this allows us to do just that. Okay, so P holds the address of Y, and we say that P points to Y. We say that P points to Y after this line. And in this kind of diagrammatic form, this is called a pointer diagram, you can express that with an arrow like this, going from the middle of P, because the value is that fact that it's going to Y, and the arrow kind of ends outside of Y, the box, because we're holding the address of Y, not the value that's inside. Okay, so the value of P is kind of like an arrow. 112, graphically represented, is this arrow pointing to Y. Okay, so P points to Y, that's how we say it. So we end up with this, and we are doing these kind of diagrams. So P is the pointer, Y, you could say it's the pointee. And so we can have this kind of arrow diagram as well, from P to Y, like I drew here. Okay, it's also possible to draw it like this, and you'll see this a lot in like maybe in your book, in future slides. You can also have something like, if P is a pointer, you'll just draw it like that. You won't have a little box for P sometimes. Okay, so maybe if I had another pointer Q, let's say, I don't have to draw a box that points to Y. Shorthand for that is Q is a pointer, it's pointing just straight to Y like that. Okay, so that's that. And let's see here. Well, what's the point of pointers, you might ask? And, well, let me tell you. It's the fact that you use, the reason you want to use a pointer is because you can indirectly now access memory at a certain address. Okay? So just like we use this ampersand, this address of operator, we can use the star again. And this is where things get a little tricky, just in terms of syntax. In a type, star means pointer. In just another normal line of code, in an expression, I'll say, star means dereference. All right, so it's the dereference operator. So just the line star P after the fact you've declared P means dereference the pointer P and get the value at that address. Okay, so what in the world does that mean? I can do things like this. I can print out P by saying star P, and I can also get the value at P by saying star P, and I can even reset it. Okay, so I can do things like cout star P. If I were to do that, this star P, what we say it does is it follows P. And goes and gets the value at the address 112. So P holds the address 112, it points to Y. And if I say star P, that means I'm following P to get the thing at that address that it's pointing to. Okay, so dereference P means go there, get the thing that's there. And that's for accessing. You can also change things by saying star P equals 5, for example. And this would cause the value at that address that P is pointing to change to 5. Okay, so this is equivalent, this first one is equivalent to, I don't know how I want to do this. Maybe I'll draw some arrows. This line is equivalent to cout Y, and this other line is equivalent to y equals 5. So star p is just another way of talking about like that and like that. Star p is just another way of talking about y at this point. We have an indirect way of accessing y itself. Okay? So that's what a pointer means. And now let's go to some code that I've written just to talk about all this stuff, just to watch it in practice. Okay, so, oh man, you kind of know what char star means now. It's like a pointer to a character. What in the world does that mean? We'll talk about that more later. It's a special kind of string, in fact. So here is my int star p and then my y. So I'm declaring a pointer to an int and an int at the same time, okay? And then I can initially print out p and see what its value is. And remember, p by itself is the address. Let me actually comment out the entirety of this file so that we just see the first line. All right, so let's do make. We'll use the default make rule. We'll say make pointers. All right, now let's make this bigger for you as well. So it's going to compile eventually, and then I'm going to run it with not/pointers, and it just so happens that p, it's undefined, right? It's undeclared. It's declared, but it's undefined, sorry. And it gets some garbage value. We got a nice garbage value, actually. Output to us in hexadecimal, by the way. It's the 0 value, and oh man, does that mean it's the null pointer? So dereferencing p is accessing the 0 address in this case, right? We don't like that. So dereferencing p when it points to garbage will most likely result in something, in a type of runtime error called a segmentation fault. Because you don't have access to that 0 address, all right? Or if it was just some random value, your program didn't have that memory allocated to it, because other programs on your machine are sharing your memory, and not all addresses belong to your one program. Okay, so now let me compile it again. Now I'm going to try and print out star p with p being set to null. And oh man, do we get a segmentation fault. So we don't ever want to do this, but that's our runtime error. So a special kind of runtime error is called a segmentation fault. A segmentation fault, or seg fault for short, I'll say, is a runtime error that you get when you try to access memory that doesn't belong to you. Okay? So you do not want to ever access null or any other address that you don't know about. Oh, oops, I should probably turn off my notifications. Sorry. Let's see here. So that's what that is. We don't like them, so try and avoid them. And now, again, of course, y is also undefined. So let's print out whatever y is set to right now. It'll be some random value as well. Oh, we're getting lucky. It's all zeros this time, but you can't expect that. It's just undefined behavior. All right, so let's actually give these things values. So y, let it hold 3 now, and let p point to y. So p holds the address of y. All right? And now let's print out all of those things. Let's print out p, what you get by dereferencing p, and then also y itself. Okay? Let me put that in view. All right, so we've actually given these things values now. So y, it's going to hold 3, and p holds the address of y. And you can see in this particular program, this particular time I ran the program, p, the address of y, which p is set to, is this long number. Okay, so it's just an address in memory. And star p follows the pointer to the location of y and gets the value there, which is 3. And of course, y is 3 as well. Okay, so star p is just another way of talking about y. And you can now use that star operator to dereference p and actually set stuff. Okay? So finally, we could do this kind of thing. We can say star p equals 5, which will go to p, go to the address of p that p holds, so the address of y, and set the memory that's there from 3 to 5. Okay? So that's what's happening there. And so, of course, p stays the same because it's still holding the value 112, which is the address of y. We never touched p, we touched star p. There's a big difference there. between resetting p and resetting star p. One is following the pointer, one is just setting the pointer itself. All right, so now star p is 5, and so is y, because y and star p are essentially synonyms. Okay? I hope that makes some sense. So with that, please take a second to do this code, go through this code in your mind, and write out the kind of pointer diagram that you get. And here we're using that shorthand where pointers don't have their own boxes, they just have arrows emanating from them. All right, so take a second to think about that. And so with that, let's talk about it. So what this is doing is it's making a pointer to an integer. P is a pointer to an integer again. You can have things other than p that are pointers, of course, but we're just trying to keep it simple right now. So initially it holds some garbage memory address. You should make sure you never dereference it. And then x is going to hold 10. And then p holds the address of x now. So let's start making up things. So this is all for pretend. So let's say this is address 100 and x's address 104, let's say. All right? So to say that p points to x, it means that p holds the address of x, which is 104. And diagrammatically, we look like we have this kind of arrow diagram. Okay? That's a bad little arrow. There we go. So now what happens when we run this line? So what it's going to do is it's going to dereference p and set the memory at that address. So it's going to change this box. It's going to change x. And what is it going to set x to be? It's going to set it to be whatever was at p's address by following it, that value there. So it's going to set x to be x, whatever that was, so 10, plus 1. So it's going to become 11. Okay? And so if we make a shorthand version of that diagram where p doesn't have its own box, we end up with b. Okay? I hope that makes sense. And I hope you got that. So with that, we just used p again to indirectly talk about x. And think about that example, that motivating example from the start of this lecture. This is going to be quite helpful. All right. Two ways of changing the value of a variable. That's essentially what we're getting right now. We have multiple ways of accessing the value that's at y. Okay? Let's see here. How do I want to say this? So yes, you can do two things. You can change y directly by saying something like y equals 5, or you can use p now because p points to y, and you can do something like star p equals 5. All right, so that's essentially what pointers give you, that ability to indirectly access a place in memory. So here is something that's going to be very, very helpful for any kind of future work you do with pointers, or maybe even on an exam. So please draw a diagram by running this code and show me the values of all the variables here. Okay? So I hope you've taken a minute to go through this and to work it out. So here is what's going to happen. So we're making space in memory every time we declare variables, all right? So we have x and y starting to be 10 and 20. Okay? I gotta be careful as to how I draw this. Let's put the pointers below maybe. So let's see here. I have p1, it's a pointer to an integer. p1 is a pointer to an integer, and it holds the address of x. All right, let's handle that first. So p1, it's a pointer to an integer. It holds the address of x. Let's make up some addresses. 100, 104. It's gonna be 108. So why not? And so p1 holds the address of x, which is in this case 100. And I'll draw these arrows later. And then p2 is a pointer to an integer, and it holds the address of y. So p2 is a pointer to an integer, and it holds the address of y, which is 104. And let's pretend that its address is 112. We'll just use decimal. And then, oh man, p3, double star. It's totally possible. You have as many pointers as you want. P3 is a pointer to an integer. So P3 holds addresses of int star variables. It holds addresses of int pointers. It's a pointer to a pointer. Okay? So in particular, P3 cannot be set to the address of x or the address of y because x and y are just ints. P3 has to point to an int star. It has to point to an int pointer. Okay? That is hard to wrap your head around, I know, but I hope you try this. Please code it up and watch it complain. So you have to be very specific with your types, and it's always the rightmost star means that P3 is a pointer, and everything else is the type that P3 is allowed to point to, the kind of variables whose address P3 is allowed to store. So P3, it is itself a pointer. Let's draw it over here maybe. P3, we got a pointer. And I don't know, let's have it hold address 116, or let's have it start at address 116. It's not necessary that these are all arranged in memory like this. It could be in weird places, but they're usually consecutive if they're right after each other like this. So P3, pointer to a pointer to an int. Initially, it's holding some garbage value, but we're then going to set it to something. Oh, and I realize, I'm sorry, I missed out this entire line right here. P2 equals P1. Let's do that before we worry about P3 anymore. So when we say P2 equals P1, we say that the value that P2 holds equals the value that P1 holds. There's no stars involved, it's just like any other variable. So look in the box for P1, put P2's, put inside of P2 that value. So P2 equals P1, change P2 to be whatever P1 was, okay? So these are manipulating addresses. It's setting P2 to a different address. So this is saying that P2 is now, no longer is 104, it's holding the address 100. So P2 is pointing to x as well now. I hope you see that. And now let's talk about P3 again. All right, so we make P3. Initially, it's set to some garbage memory address. And then we say that it holds the address of P2, okay? Which means that P3 is going to hold the address of P2, which is 112. So P3 points to another pointer, okay? All right, so now with all that, let's draw our arrows. And it's important to, I really recommend, and I should put this over here just to make it clear, I really recommend that when you draw your first few pointer diagrams, or even on the test, when I ask you to draw a diagram, that you make up addresses and draw arrows at the last possible opportunity, so at the very end. Okay? I really recommend that you do that because it really helps with getting these arrows correct. So we're saying that P1 is pointing to x like there, like that. P2 is also pointing to x. And then P3 is pointing to P2, just like that. Okay? And it's possible that you can confuse yourself, and we'll have a question about that on a future slide. If you don't do this process of making up addresses and drawing arrows at the very end, you might confuse yourself about where an arrow is supposed to go. And I've seen that a lot, and I just want to highlight that right now. Okay, so that's that. Isn't this cool though? Should I? Yeah, let's continue. In this particular diagram, notice that there are 3 different ways of talking about of resetting the variable at address 100. There are 3 different ways of actually 4. 1, 2, 3. Yeah, there are 4 different ways, sorry, of changing the value, accessing the value at address 100 in this example. Isn't that cool? You could say, here are your options. You could say x equals 5. You could say, because P1 points to x, you could say star P1 equals 5. P2 points to x. You can say star P2 equals 5. P3 points to P2, which points to x. So you can say star star P3 equals 5. Your 4 options. Isn't that cool? All right. Pointers to pointers are actually kind of useful. And in fact, your main function can be rewritten from char star argv bracket bracket to char double star argv. Ask me about that in office hours, and I would be happy to explain it. All right, so moving on. All right, right now, please go through this, run this code in your mind on paper, and draw a diagram and see which one best represents what's going on. And this is actually a perfect example of that kind of error that might happen, okay? So right now, you can rule out one of these two options, A and B, by the types themselves, all right? So P1 is a pointer to an integer, P2 is a pointer to an integer, and X is just a normal integer. This diagram for B, this diagram for B is saying in order for P1 to have an arrow this way and P2 to have an arrow this way, P1 better be a pointer to an integer because X is an integer, and P2 better be a pointer to an integer because X is an integer. And that is in fact true based on these types. But here, A, you can rule out immediately actually because, yeah, P1's a pointer to an integer, but P2 is also a pointer to an integer. The only way that the compiler would ever let you have P2 point to P1 like this is if P2 were a pointer to an integer, if there were 2 stars here, okay? So you cannot even think about this being an option, okay? And that is exactly why I encourage you to make up addresses. That kind of error is quite common when you're starting out. So let's do this. P1, P2, and X, all right? P1, P2, and X. And let's say X has address 100. Don't really care about P2 and P1 addresses right now. So P1 holds the address of X. It didn't actually give X a value, doesn't really matter, I guess. P1 holds the address of X, so P1's going to hold 100. And then we say P2, whatever, we're going to set P2's box to hold whatever P1's box holds. All right, that's how we're reading that. So P1 or P2 holds 100 as well. All right. Notice that when you draw arrows now, after you've made up these addresses, it looks like this. Not like that, okay? Because P1's address is definitely not 100. It could be like 104, 108 over here, for example. So that is not what's going on, all right? And if you make up addresses and draw arrows at the last possible second, you will not make that mistake for A, okay? So I encourage you to make up those addresses. So the answer is, in fact, B. Okay. But please, in any real example, give X an actual value. All right, so now, going back to the very beginning, we finally are able to do that actual swapping, okay? So instead of all this stuff going on here, we didn't like the fact that X got copied, Y got copied. We didn't actually touch this A and B. Well, let's use pointers. Let's do pass by address. Because initially we were just passing along copies, and that's called pass by value or call by value. This is like pass by address or call by address when we use pointers. So here's what you want to do. I'll zoom in. The idea is you put stars everywhere, right? So it's going to be in star X, in star Y. Temp is an integer, but it's going to hold, if you want to get the integer out of X, which is a pointer to an integer, you have to dereference it, things like that. So, and then when you pass things along to swap value, you have to pass along the addresses of those things, all right? And that is going to allow X and Y to point to A and B, and you can actually get at those values when you dereference them. So let's draw that stack diagram one last time. So again, we have main. We had X, and we had Y. No, sorry, it was A and B, in main at least. A and B, and then it was 30, 40, right? Yep. 30, 40. And then when we call swap, we have some variables inside of swap. It's got local variables x, y, because parameters count as local variables, and temp, x, y, and temp. There we go, there we go, there we go. And remember that these are addresses. X and Y are pointers. They're going to hold addresses of things. So let's pretend that the address of A, well, my favorite address is 100 and 104. So X is going to hold 100, Y is going to hold 104 because we're passing along the address of A and B for X and Y. And yeah, so that we have this kind of situation going. We can talk about things between stack frames. That's lovely. All right, and then temp, of course, is going to be star x. So get the value by following x and what's there. So temp becomes 30. And then we do this swapping by setting star x to be star y, like this. So follow x, reset it to be star y, which is 40. And then we set star b, or star y, which is b, to be whatever temp was, becomes 30. And so even after this, this function returns back to main, we actually did some progress, or we made some progress, and we reset those things that we actually wanted to reset. Okay? So that's beautiful. That's exactly what we wanted here. And now let's talk about something very similar, but still quite different. So the idea is arrays and pointers go hand in hand. If you remember from last time, there was this weird catch where if you passed along an array across functions, you were able to change those things, those values inside that array. The array itself did not get copied. And the idea behind that is that arrays are in fact pointers under the hood. An array is a pointer to the first element, you can say. All right? So if I make an array in C++, AR, if I make it be 20, 30, 50, 80, 90, let's say, in C++, it'll look like this, right? It'll be like int AR equals 20, 30, 50, 80, 90. And the idea is, sure, you can access AR0, AR1, things like that. But actually, if you pass along AR, just like you did, no, I'm sorry, I have to do this as well. When you pass this to a function, like you say foo AR, you say AR without any brackets. And the reason for that is AR, by itself, if that's the name of your array, is a pointer to the first element of that array. Okay? So if this array starts at address 100, AR is really just a pointer to 100. So AR, instead of drawing it like this, 20, 30, 50, 80, 90, this is address 100, 104, let's say, because ints are 4 bytes long. And I should probably say this now. For this class, we'll assume that we're on a 32-bit processor. We'll assume 32-bit addresses. So pointers, that means that every pointer takes up 4 bytes. And that's not true on most of today's computers because we use 64-bit processors now and 64-bit machines, but it makes things a bit easier just to assume this for this class. All right, and ints are also 4 bytes long. Okay, so AR is a pointer to the first element, which means that you could write it like this. You can put AR's name right there, or you can put it like this. You can say that AR is just another pointer. It holds 100, and it's pointing to that first element of the array. Okay? So the beauty of that is if I want AR0, I can also get at that by just dereferencing AR. Do you see that? 100, AR0 is essentially that. So this means that the address of AR0 is equal to AR. Okay? It's two ways of talking about the same thing. And you can also use this thing called pointer arithmetic to get at the things that are later in the array. So AR2, we say it's equivalent to dereferencing AR and then adding 2 after adding 2. So address, the address of AR2 is equivalent to AR plus 2 dereferenced. So this is called pointer arithmetic. Is when you add numbers to a pointer. And the idea is it knows how big that type is. Because AR is a pointer to an int, remember that AR is just the first address of this array, the C++ compiler knows that 1 after that AR is really 4 bytes later. Okay, so if you add 1, if you say AR plus 1, it's going to give you address 104. So AR plus 1 in C++ is really AR plus 4 in the final program. And so AR plus 2 is really, this is the address, AR plus plus, AR plus 4, the address, AR plus 8, because every integer is 4 bytes, so it's kind of multiplying this by 4. So AR plus 2 in code is going to get you 2 after AR, so it's plus 1 is there, plus 2 is there, so it's really address 108. Dereference that, we get this value here. All right, so that's going to take some practice, but pointer arithmetic is quite powerful. You just got to make sure that in your arrays you shouldn't ever go past the end of it, just like any other thing. Okay, so there's another way, another kind of syntax that's essentially what this bracket notation translates into. It really translates into a pointer dereference after an addition of a certain amount. Okay, that's the idea there. So with that, do I want to go here? Yes. So let's do this first, and then I have a piece of code that I've written just to demonstrate all these things, and we'll go to that. So what this is doing is it's making ARR this time. It's 50, 60, 70. So we're going to make an array called ARR. That's going to hold 50, 60, 70. And remember, ARR is really a pointer to the first thing. All right, you can think of it like that. And let's say the address of these are 100, 104, 108. And then in start P, okay, totally fine. We make a P, that's a pointer to an integer. And it's going to hold whatever thing ARR holds. And remember, ARR, when you say it by itself without any brackets, is a pointer to the first element of the array. Okay, so it's going to be the pointer to that 50. So whatever the address of 50 is, it's 100. Because ARR is really a box holding 100, essentially. All right, so P pointing right there. Let's make that start from the middle. There you go. And all right, P equals P plus 1. There are no stars. So this is saying P, the box that holds an address, we're changing that address to be whatever it was, plus 1 more. And because P is a pointer to an int, we're going to increment not by 1 byte, but by 4 bytes, because the compiler loves us. And it knows what we're really talking about is the next int, plus 1 int, not plus 1 byte. All right? So P equals P plus 1 will do this. It'll set P to point to that 60 now, to hold address 104 instead. All right? So instead of 100, it's going to hold 104. And now this is saying, all right, go to that address, get the value there, and increment it. All right, so this is going to make it 61. All right, and I hope that makes sense. And before we go to the next slide, I have some code to just go through all of this. So the idea is essentially this. We're going to make this array called ARR, just like we did. It's going to hold 50, 60, 70, totally fine. And remember that ARR is an array and it holds integers. You can also make arrays of pointers, totally fine. Here's an array of pointers to each of the values inside of ARR. So here's an array of pointers to integers. This is starting to make more sense, isn't it? Initially the first address of the array, address of the first thing in the array, address of the second thing in the array, address of the third thing in the array. So it's an array of pointers to another array, which is weird, but you can do things like that. So now, what we can do is, well, first, how about I print out the addresses of everything in that array, and let me comment out everything else. So here what I'm going to do is I made this array. Let's print out the address of all of these things in the array so we can watch it. All those things get incremented by 4, right? So make pointers and arrays. All right, so this is in fact incrementing by 4, but this is the starting address, the first thing, ARR0, the address of that. Plus 4 is this one, plus 4 is that one. So those are the addresses of those 3 elements in the array in consecutive order. And of course we can print out the array. It's still 50, 60, 70. That should make perfect sense. Cool. All right, let's continue. Let's do those things we were doing. So let's make P. P holds the address of the first element of ARR. So you could also have done this. P equals the address of ARR0, because ARR by itself is the address of its first element. Okay? P equals P plus 1. Remember, it knows that you're trying to get to the next int, one more int, not one more byte, so it's going to add 4 bytes to P. And then we're going to increment the value held at the address that P points to, right? Which is going to be the address of the 60, right? So then, what's going to happen is that increment is done now, and if we print out this array, we should see exactly what we talked about here. 50, 61, 70 now. Okay. So with that, let us. I can't really put everything there, but it should make sense that this got changed to that, and that is the idea of pointers and arrays at the same time. All right. Let me check my time. We're doing pretty well today. All right, so now onto this slide where take a second and see if you can think of, you can imagine this code is in main, just somewhere that it's allowed to be, and it's running, and it's allowed to call this function, increment PTR. All right, so see if you can figure out what's going to happen after this is called in that code. All right. So, I'm sorry about the noise, by the way. What's going to happen is, let's pretend that we did all this in main, all right? So, let's see. I need a lot of space. So let's pretend we're in main. Main's got a lot of local variables now, doesn't it? Main has an array to its name, so it's got ARR that lives inside of it. This might not be the best idea, but we'll make it work. 50, 60, 70. 60, 70, tiny. All right, and then Q is going to be a pointer to an int, and it holds ARR, which is the address of the first thing in the array. All right, so Q, let's pretend it starts at address 100, and now I wrote way too small, but I hope you understand what I'm doing. So Q holds address 100, and it points right there. All right, now I want to increment PTR Q. All right. So we have this going on, and we want to call this function now. So the idea, or the question is, does Q change? And that's essentially what these two options are. Either it changed to the next one, or it didn't. So let's talk about what's going to happen when we call this now. We're using pointers, so maybe it gets changed. So I'll call it increment. And the increment's local variables are just its one parameter P. And P holds whatever Q held, which is 100. So P is pointing to, maybe I'll use green. P is pointing to that 50 right there. Okay? Let's do that. All right, then p++. Okay, p goes to the next integer. It holds 104. Oh man. Well, yes, p no longer points there, it points here. But look what happened to q. Absolutely nothing. And this is another example of this exact problem that we had at the beginning. We wanted to change things and we passed along the things of the same type, and they never got changed because they just got copied. So the moral of the story here is we wanted to change a value of type int star. We should have passed along a pointer to an int star star, because right now we didn't change a darn thing, and q is still pointing to the first element. All right. So the solution here is you always got to go one level higher, right? So if we go back to here, we went one level higher. We wanted to change integers, so we passed along int stars. Now we want to change int stars. Oops. Now we want to change int stars, so we got to pass along int star stars. And this is going to be beautiful. Let's draw this now. Excuse me. All right. What should we change this line to be now to make this do the right thing? All right, so we don't want p++ anymore. So technically you can get rid of a. So think about this for a second. What should we change it to? We know we need to do this now. We need this kind of setup. Let's see if I can copy this. Ooh, I want to select with the lasso. Whee. All right, copy. Please paste lower. There we go. All right, so here is the new version. Let's see how much I am allowed to erase. Yay, that is useful for me. All right, so p, remember it's a pointer to a pointer, and let's say that q's address is 112. So we're going to pass along the address of q now. That's a difference as well. Pass along the address of q now, so that p holds the address of q. It's a pointer to q, 112, and it's going to point just like that. So we're allowed to actually change q at this point. So now, I encourage you to code this up, by the way, and see what actually compiles, because a number of these won't even compile. Specifically, this will work. It'll just change p to be the next thing. Oh no, sorry. Yeah, this is the only one that doesn't really make any sense, because we're setting the address of p, which is not the right type, back +1, which is like a pointer to pointers to a pointer, +1, trying to store that as a pointer to an int. The types get weird, and the compiler will complain appropriately. But the idea is what we want to do is we want to use p to change q to be one more, like that. Let me draw that in a different color, by the way. We want that kind of thing going on. We want it to be 104, right? To hold 104 so that it points to the 60. And the way to do that is we can't reset p. We have to follow p to get to what's there. Yeah. So we gotta reset, not p but star p, right? All right. So follow what's there, set that thing. We need to set it to be, well, it's 100. We just gotta go one more int. All right. So start with 100 plus one more int. All right. I hope you see that. And that means that c is in fact the correct solution here. If you code that up and print things out, everything should go all right. All right, we're getting there. We're getting to the end. So let's step back for a second. So there are two things that this slide is talking about. So the first is a pointer. You have to be very specific when you're making your pointers. You have to say what kind of thing, what the addresses that it's going to hold, what types those are going to be. So you have a pointer to an int. That's what we've been using all day long. You can also have pointers to characters. So jar star c, for example, it can be a pointer to a character, or a pointer to a character. You can have multiple stars. Structs we'll talk about later. You can have pointers to other pointers, pointers to doubles. And remember that it's just like another place in memory. If you initialize it and don't, if you declare it and don't initialize it, Well, it's not pointing to anything, so it's holding a garbage address. So you should do a few things. One of a few things. You should make it point to something that you know about. So give it an address that you know is there, address of some other variable. Or you can let it hold null and just make sure that you always check so that you don't dereference null. Make sure that it's eventually going to point to something that isn't null. So you can have if statements that do that. You can also do something that we're going to talk about later, is you can allocate memory, allocate a new thing of that type. So if this is a pointer to an int, we can allocate a new integer in a place that we haven't learned about yet. So we've been making memory, and it all lives on this thing called the stack. It belongs to whatever function we're making our variable inside of. We can make it on something called the heap, and we can do this. So that's a way to get at an address that we can use. Those are your options. So make sure to use one and not dereference something that's weird, like something that's uninitialized or null. And then we also talked about pointer arithmetic, and just to go through it one more time, just to spell it all out. So we have an array of large things, of different types. So if we had an array of doubles, if we had an array of integers, an array of pointers, whatever the type is that's involved, all we have to do is add 1 to get the next thing of that type. It follows like the guidelines of how big that type is supposed to be, and so instead of plus 1 byte in memory, it's going to add 1 times the width, 1 times the size of that particular type. So if it's an integer, ptr plus 1 is going to get at the next integer in memory, which is the 4 bytes later. So the address plus 4, really. Right? So it adds the size of that array element. And so it knows, because we declare up front, that's one of the reasons we do it. C++ is going to know the size of everything that your pointer is going to point to. Okay? And therefore, this kind of arithmetic is always going to make sense and is always going to be correct, because we declared the types that those pointers can hold ahead of time. So if we say ptr plus 1 and we have pointers to characters, well, yeah, for sure, it's totally going to do just 1 byte next, 1 byte later in memory. Whereas if it was an integer, ptr plus 1 would be 4 bytes later. Or if it was a double, it would be 8 bytes later, and so on. So that's one of the beauties of using these types everywhere instead of something like Python. And of course, with great power comes great responsibility. So if you have pointers and they are just addresses in memory, they hold addresses in memory, you can totally set up a pointer to hold a weird looking address, one that you do not have access to. And every time you do that, it's going to result in either undefined behavior and the program continues, you'll just get weird things that happen, or usually you're going to have a runtime error, that segmentation fault thing. All right, and a segmentation fault is just, it's a runtime error. That means you try to access memory that you don't have access to, or it just didn't exist in the first place, in the case of the null pointer. All right, so that's a lot of words. I hope that it makes at least a little sense, and you're going to get plenty of practice with this in later lectures and your labs, of course. Okay, and in homework. So then, finally, now that you know a little bit about pointers, you should be able to chuckle slightly at this comic, and everything should make a little bit more sense. And with that, I think we're at the end of our slides, and that's all I had planned. So I'll see you next time.